Welcome to the video lesson for Thursday, October 15th and Friday, October 16th. So we started class with a pretty fun warm-up. I said that Northwest High School is getting our badly needed addition, and while excavating, we found an entire buried ancient town in the middle of Germantown. So what are some ways that archaeologists could figure out how old the artifacts were that were found in the town? And you can see Mr. DeAndre and Mr. Asensio are both pretty surprised at what we found. So I got a lot of different answers, and the one we're going to talk about in this lesson is actually carbon dating. Then the second part of our warrant was about half-lives, a nice little review of what we went over on our last class. So how many half-lives have passed for each of the following samples? Well, if I have half or 50% of my original radioactive material, that means that one half-life has passed. Then B, 25% of the original sample remains. Well, one half-life cuts 100% down to 50. Then a second half-life cuts 50% down to 25. So that's two half-lives. And then C, if only 12.5% remains. Well, one half-life cuts 100% down to 50. A second half-life cuts 50% down to 25%. Then a third half-life cuts 25% in half into 12.5. So C would be 3 half-lives. Your homework is to finish the Half-Life app assignment. So going to the Syllabra app's Half-Life problems, practice problems, getting a score of 10, and handing in a image, a JPEG, of your entire browser screen to show that you got your 10 points. That's due in our first class next week. And the carbon dating packet was given out today in class, and that is also due at the beginning of class for the first class next week. After our warm-up, we finished our notes for Unit 2 by taking notes on carbon dating. Then we did a graphing activity for carbon dating to kind of illustrate what's going on. And then you got time to work on one-on-one breakout rooms by yourself. So you could call on help for individual help if you needed it on half-life, on the carbon decay packet, or if you just need a little bit of class time to make up that last nuclear decay exit card, if you haven't had a chance to do a retake yet. So in our Unit 2 notes, we have 2 different videos about carbon dating. There's this one and this one. In class, we watched How Does Radiocarbon Dating Work? I highly recommend you watch the second video as well, although we did not have time for it in class. And I'm going to go ahead and play it right now for us.
How do we know how old something is? For people, we'd ask to see their birth certificate. For trees, we'd count the rings. But how do we know how old a fossil is? Fossils have their own internal clock. Scientists can read it by looking at the ratio of 2 different types of carbon atoms. Of course, every living thing is made of carbon. Plants grab carbon dioxide from the atmosphere and use it to form complex organic molecules. Animals get their carbon by eating these plants. But there's more than one form of carbon. Most carbon atoms have 6 protons and 6 neutrons. We call this carbon-12. High up in the atmosphere, sometimes cosmic rays hit nitrogen atoms. This creates carbon with 6 protons and 8 neutrons. We call this carbon-14. Carbon-12 and carbon-14 behave alike, but carbon-14 has one unique and important attribute. It's unstable. So once an animal dies, the carbon-14 in its body will start to go away. Every 5,730 years on average, about half of the carbon-14 atoms will decay into nitrogen. This is its half-life. After one half-life, the animal will have about half the amount of carbon-14 it started with. After another half-life, it will have about a quarter. And after another half-life, it will have about an eighth. By contrast, the amount of carbon-12 it has in its body will stay the same. By measuring the ratio of carbon-14 to carbon-12, we can measure how many thousands of years have passed since the animal died. Carbon dating works for fossils up to about 60,000 years old. For older fossils, scientists use unstable elements that have much longer half-lives. For Scientific American's Instant Egghead, I'm Michael Moyer.
So then on slide 15, we summarized what was in the video and just kind of brought all of our ideas and main points back together about carbon dating. So carbon dating is a form of radiometric dating. All radiometric dating techniques relies on two isotopes of the same element in order to work. These isotopes that you're using and depending on have to exist in known ratios. For carbon dating, it has to exist in a known ratio in living tissue. There are some elements that you can use non-living items on, but for carbon dating, it can only be used on organic things. One of those two isotopes will be stable, which means it does not go through nuclear decay, and then the other isotope is unstable, so it decays at a known rate. So the stable one does not change. However much of that isotope something has at the time that it dies does not change. It is consistent. But the unstable isotope will decay over time. And for anything that we're going to use for radiometric dating, we know the half-life. We know how long it takes it to decay. So since we know how much of the stable isotope is there at the end when we uncover organic remains, we also know how much of that stable isotope was there when the artifact died. So if I know how much there was at the beginning of my stable isotope, and I know the ratio of the stable to unstable isotope, I can figure out how much of the unstable isotope I should have had at the beginning when my sample died. And I can compare that number to what I know it should have had to what it has now, and then we can see how many half-lives it took for the mass of that unstable isotope to decrease to what it is today. So carbon dating is one that we look at a lot, and it relies on the carbon-12, which is one of the most stable elements in the entire periodic table, and carbon-14. Then on slide 16, we have an example problem for carbon dating. Now, it looks a little bit different on your slide because there's a bit of a translation error going from the Word document to the Google Slides, but here's the correct form. So if a sample is found to only contain 25% or 1/4 of its original carbon-14, how long ago did it die? And the half-life of carbon-14 is 5,730 years. So to solve this, we need to solve A and then B. So A says, if 25% of the carbon-14 remains, how many half-lives have passed? So notice, this is just like how we did it last lesson. We always solve for the number of half-lives first. So 0 half-lives gives me 100%. 1 half-life brings me down to 50%. 2 half-lives brings me to 25%. So 2 half-lives have passed if I only have 25% of my original sample. So now, if each half-life is 5,730 years, how much time has passed? So I know that I have 2 half-lives, and I'm going to multiply that by 5,730 years. Now you can just plug it into your calculator like this, but I'm a bit of a stickler for units. I don't like this half-life times years, so I'm going to divide by half-lives. So there is 5,730 years in 1 half-life. Dividing by 1 doesn't change my answer, so you can skip this step for now if you want. I'm a stickler for units. I like to make sure my units are good. So 2 times 5,730 means that the time that has passed is 11,460 years. And then another way to solve this is there was actually a graph here that showed you percent of carbon-14 remaining. If you go down to 25%, that means 11,460 years have passed, approximately. So next, I wanted to illustrate what's going on because I know for a long time, it was really hard for me to figure out, wait, how do you know how much there's supposed to be when it died? No one was there. How can you be so sure of that? So I've got this graphing activity, and we're going to make some assumptions that are kind of wrong, but we're going to make these assumptions because it makes our math a little bit easier and a little bit easier to show. So we're going to pretend that the ratio of carbon-12 to carbon-14 is 50%. So for every one carbon-12 I have, I also have one carbon-14. Now that's a lie. It's more like there's 1 trillion carbon-12s for every one carbon-14. But to make our math a little bit easier here, we're going to say it's 1 to 1. And instead of using a half-life of 5,730 years, we're going to round that to 6,000 years. Again, this is just to make it a little bit easier for our graph. Because the point of this graph is to make this more visual, what's happening. So the first thing we need to do is make a key. So I'm plotting all of my carbon-12s with red and all of my carbon-14 amounts in blue. So at the very beginning, when my sample first dies, at year 0, we're assuming that I've got a bone that starts with 320 grams of carbon total. So if it's 320, and we're going to say it's 1 to 1, half of it is carbon-12 and half of it is carbon-14, that means my bone, when it first dies, starts with 160 grams of carbon-12 and 160 grams of carbon-14. So I've got a red and a blue there at the same time. Now, after 6,000 years takes place, that's 1 half-life for carbon-14, my carbon-12 is still 160. And my carbon-14, its half-life is 6,000 years, so I'm here at 160. I'm going to half it down to 80. So 80 grams in 6,000 years is right here. Then we're going to jump ahead another 6,000 years. So after another 6,000 years have passed, I'm at 6,000. Now I'm at 12,000 years. My carbon-12 is still 160 grams. But my carbon-14 is unstable. It's going through nuclear decay. So I had 80 grams. Now I'm going down to 40 grams. So every 6,000 years, my amount of carbon-14 is going to half. But my carbon-12 is stable. It does not decay. So my amount of carbon-12 doesn't change as the years go on. So another 6,000 years comes to pass. I was at 12,000 years. Now I'm at 18,000 years. So go up on my graph and I make a dot here for my carbon-12. My carbon-14 was at 40 grams, but now another 6,000 years have passed. So I'm going to go down to 20 grams and 18,000 years. Then another 6,000 years, so from 18 to 24,000 years since my sample has died. I still have 160 grams of carbon in my bone sample. But at 18,000 years after my sample died, I had 20 grams. So now I'm going to cut that in half to 10 grams. Then another 6,000 years comes to pass. So 30,000 years after my animal has died, I still have 100% of my starting amount of carbon-12. My carbon-12 doesn't change over time. It's stable. It does not decay. But now, what was once 160 grams of carbon-14 is now all the way down to 5 grams. Then I encourage you to try and connect the dots to make this a line graph, and bear with me, it's not super easy to annotate online. And notice this is not a linear slope. That's an exponential curve there. And then my carbon-12 is just a straight line across. So then we filled out our table. Now, almost all of the values for this data table are right next to me in the graph. So my original amount of C14 was 160 grams. That's what I started with in my graph. Then after 6,000 years passed, I was down to 80 grams. Then after another 6,000 years, I was down to 40 grams. Then another 6,000 years passed, I was down to 20. Then after another half-life, I was down to 10 grams. Then my graph only went to 30,000 years, and so I stopped at 5 grams. But I think we can all figure out that if I could go another 6,000 years, I would be down to 2.5 grams. Now, a nice thing about doing this in person with string is when you fold the string in half and cut it in half every half-life, we don't cut string in half perfectly. So students would actually have to measure their string against here, and you get slightly off numbers. You might not get exactly 80 grams after one half-life. You might get 78. You might think it's closer to 85, and that's okay. It's not precise. It doesn't mean exactly half of it's going to go there. It's about half will have decayed by then. This is not exact, but it gives us a good idea. So 100%, after one half-life, we're down to 50%. So 2 half-lives brings us to 25%. 3 half-lives brings us to 12.5%. 4 half-lives brings us to 6.25%. 5 half-lives brings us to 3.125%. And then 6 half-lives, we are down to 1.5% of our sample is left. Now the percents are pretty easy. You just divide the previous percent by 2. But personally, I find the fractions even easier because when I half a fraction, all I do is multiply the denominator by 2. So I had 1 over 2, 1/2. After 2 half-lives, that's 1 over 4. Then 1 over 8. 4 half-lives is 1 over 16. 5 half-lives is 1 over 32. And 6 half-lives is 1 over 64. And then my carbon-12. At 0 years, when my sample died, I started with 160 grams. That's rather small. Let me make that bigger. Then, after 6,000 years passed, I now had 160 grams of my carbon-12. Then, after 2 half-lives had passed, my stable carbon-12 had 160 grams. And it stayed 160 grams through all of those half-lives. Remember, 6,000 years was the half-life for my unstable carbon-14. My carbon-12 is stable. It's not going to decay over time. So my percent of carbon-14 compared to what I started with also stays at 100%. So to do this quickly, copy, paste, 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 paste. Oh, what just happened there? Paste. And my fraction, oops, looks like it didn't get deleted after the last class, also stays the same. It's 1 the entire time. So my carbon-12 does not change. It's my carbon-14 that changes. So if I'm digging in the backyard and I find a bone and it has 160 grams of carbon-12, according to this, and we're assuming it's 1-to-1, then I know that whenever it died, it started with 160 grams of my carbon-14 as well, because my carbon-12 doesn't change. And if my ratio is 1-to-1, then however much carbon-12 I have, that must be how much carbon-14 I started with. So I can look at what I have. So if I dig up a bone with 160 grams of carbon-12 and only 5 grams of carbon-14, I know I need to figure out how many half-lives took place to cut 160 down to 5 grams. Now, the real numbers we work with are much different because it's about less than 1% of your total carbon is carbon-12, so it's a much more askew ratio. But it's the same principle, just the numbers work out differently. So a few quick notes about your carbon-14 dating packet. So here it goes into much more detail with the correct ratio of carbon-14 and its other isotopes. And it also uses the correct half-life for carbon-14, the 5,730 years. Now, when you get down here to the second part, applying concepts, you're asked to label these rocks as which one is fossil A, B, C, and D, but you can't actually write on top of there. So what you need to do is go to Insert. So make sure you've got your cursor down here. Go to Insert, Drawing, New. Go to this line tool, and what you want is scribble. So then just write your letters in the order that they go. I'm going to say A, B, C, and D. And I'll also give you this quick hint that that is not the correct answer. Save and close. So then I've got my answer right here next to the question. You can't place it on top of it, unfortunately, but you can just write it right next to it. And using that drawing tool is also how you might want to show your work for other problems. Here it's asking you to justify your answer, so it isn't quite the same as showing your work. For instance, there's 5,300 years. So what percent is remaining? 5,300 years is not easily or evenly divided by the half-life of carbon. So you probably can't give me an exact answer for what percentage, but you should be able to tell me about how much is still left of the carbon-14 in that bone sample. So tell me how you can figure out what is the approximate answer to that question. So that's all that we covered in class today. We spent the last few minutes working independently so you could call for help from one of your teachers or focus on retakes or just get started on your carbon dating packet. Don't forget, we are handing out physical paper copies of the periodic table at Northwest High School during lunch pickup times. Might as well go and get a free lunch while you're at it, as long as you bring your student ID. And there are also extra practice problems of half-life that you can work on in the module. Now it says optional. There are no points that you can get. The answer key is there in that optional assignment, but it's more practice. Remember, you can always find me during the student support and activity periods and the Wednesday check-ins. I'm always in my office hours Zoom. So until I see you guys again, make good choices and stay safe.